Well, hello there. My name is Andy Foster. I'm a light sport flight instructor, commercial instrument pilot, and I have a bachelor's in aerospace engineering. And we're going to talk today about Newton Bernoulli wings and lift and how they all act together to make an airplane fly. Now, when I came up through pilot training and first started learning about aerodynamics, of course, I learned how lift works, and it was all based on Bernoulli's equations. Since then, there's been an educational effort to essentially incorporate more of Newton's laws into this explanation, and actually it's kind of gone awry because a lot of the explanations that you see out there that especially that talk about Newton's third law are actually incorrect when you start talking about the actual mechanics of what's going on in the flow field. So let's start talking about Bernoulli's, because that's where everything kind of started. Even in books, you'll see like the Aerodynamics for Naval Aviators, which is a really good and but an old text. It talks about Bernoulli's to explain lift, and essentially Bernoulli's equations simply describe the relationship between velocity and pressure in a flow field. Now, there's two types of pressures that you worry about. One's called the static pressure. That's the same as the atmospheric pressure, or the pressure of the air when it's not moving. And then there's dynamic pressure, and that is the pressure essentially that you would measure by wind hitting you in the face. And in 1738, a scientist named Daniel Bernoulli essentially wanted to understand these pressure and velocity relationships, but he wasn't looking at air, he was looking at fluids, but air is a fluid. And he came up with a concept where he started looking at the relationship that develop along air moving on what's called a streamline. Now, a streamline is essentially a line that's drawn by taking one point and drawing a line that's tangent to the velocity vector of air that's moving at that point. And then you connect all the dots and it makes a line. And that's in this picture that you're looking at, what you're seeing are streamlines flowing around a non-moving ball. And he used Newton's second law, which is F equals ma, to calculate the relationship between velocity and pressure for an air particle moving along a streamline. Now, in this drawing you see here, there's a P1, V1, which is pressure and velocity at point 1, P2, V2, pressure and velocity at point 2. And when you look at the relationships at those 2 points, and you see the streamlines are squeezing together here as they go over the top of the ball where P2 is, well, when you see streamlines squeezing together, that's telling you that the air is accelerating. If they're equally spaced, the air is not really accelerating or decelerating. And if they're expanding, then the air is slowing down. And so for this particular drawing and these 2 points, P1 and P2, what Bernoulli's law, which we'll look at in just a minute, is telling us is that the pressure at point 2 is actually the static pressure, and that's the pressure perpendicular to the flow field, and i.e. the static pressure. That static pressure at point 2 is less, and the velocity of the air that's actually moving is more. So here's Bernoulli's equation. And what Bernoulli's equation really says is that any particular point, the static pressure, which is the P on the left side of the plus sign, plus the rho, which is the density of the air, times the velocity squared divided by 2, and that is called the dynamic pressure, is equal to a constant. In other words, the static pressure plus the dynamic pressure at any point in a fluid is a constant. So what that tells you is that as the dynamic pressure increases, the static pressure decreases, and vice versa. Now, a lot of aerodynamic tests, if you're reading them or you're talking to especially pilots or test pilots, they may start talking about Q or Q bar. That's dynamic pressure, which is the rho v squared over 2 term. And again, as I've already mentioned, the static pressure, or the P in here, is the pressure measured in the direction perpendicular to the flow, and in airplanes, that is the atmospheric pressure. Now, Bernoulli's relationships, and talking about lift with Bernoulli's equations only, is accurate from a very simplified point, in that if you take an airfoil, which is a picture that we have here, a cross section of the wing, and you put it in a wind tunnel, and then you measure the pressure all around it, you'll get a plot that looks something like this graphic that you see on the page. Now, the actual shape of these pressure fields, on the top is trying to show you low pressure, and the bottom is showing you high pressure. And what you can see is there's a big low pressure area on the top and then a smaller high pressure area on the bottom. And the graphic is correct in terms of the shape of the flow fields and the relative sizes, but it's incorrect in that it's showing the arrows pointing outward. Obviously pressure is a push always, and so what really, there's no way you can really draw it using the way that they've done it that really shows all that in one sense. So in other words, pressure is always a push, it doesn't really pull, though my aerospace engineering professors used to joke about it and say the wing is actually sucked up from above. That's not actually accurate either, but it's a nice little joke. But anyway, you can just take the pressure, measure it at each point, and then use Bernoulli's equation to essentially calculate how much lift force that wing is generating. And actually, as a beginning aero engineering student, that's what we did, just to show us that, yeah, it really does work. Now that gives you the right answer and this is for pretty simple aerodynamic flow actually, but it doesn't really fully explain or capture all the fluid mechanics that's going on in the flow field. And as we'll talk about in a minute, that's actually a very complex deal. So what I want to emphasize first before we talk about anything else is lift is the force generated by the difference between those two pressure forces, the low pressure area on top and the high pressure on the bottom. That force imbalance is what we call lift. And of course it's in relation to the airfoil, not relation to gravity. And that's how we can fly airplanes upside down, and we'll talk a little bit more about that. And what the graphic is showing you is that there is a point on the airfoil, and actually where the lift acts or seems to act through a specific point, and that point's called the aerodynamic center. And so you should see in any drawings where you're trying to show the lift acting on a wing, it should be at the aerodynamic center of the airfoil. And for most subsonic airfoils and small airplanes we fly, that's about 25% the length of the airfoil from the front. Now we talked about what streamlines are, and this is showing you, this is assuming a flow from left to right, and this is the air that flows around a non-moving ball. Okay. And as you can see, you can see the streamlines squeezing together, but that raises a very interesting point that we'll talk about in a minute, that if you look ahead of the ball, you'll see the streamlines are actually starting out to move away from the ball before it ever gets there. So what is that telling you? And we'll talk about that in a few minutes. So we looked at what happens when you put a ball in there. We're going to take a shape that that's like an airfoil or subsonic airfoil. It's kind of shaped like a teardrop. That's the most efficient shape you have for these kind of airflows. And we're going to talk about what happens when the air moves past it. Now, the airfoil that you see, if you take a line from the leading edge to the trailing edge and you cut that in half, the top and bottom are shaped and sized exactly the same. When you do that, you're building what's called a symmetrical airfoil because its upper and lower halves are essentially symmetrical. And if we take that symmetrical airfoil and we put it in an airstream that's moving, again, the picture assumes left to right, and we put it at 0 angle to the airstream, we're going to get a flow field that looks like the picture. And notice that the streamlines above and below the airfoil are equally spaced. So that's telling you that the static pressure both above and below the airfoil are equal. In other words, there is no pressure imbalance, which means there is no lift. Okay. But if we take that symmetrical airfoil and we incline it to the airfoil, to the airflow, and this picture is showing us about a 9-degree incline to the airfoil, to the airflow, then the streamlines bunch together at the top, push away a little bit at the bottom, they kind of expand a little bit. But if you look at what that's telling you, you're getting a much higher velocity over the top of the airfoil and a lower static pressure, and with the expansion down below, you're actually getting a little high pressure area below the airfoil, which means the air is actually slowing down a little bit. And overall, if you look at the overall kind of direction of the airflow, you're getting a big curve over the top, and that's what's shown in the bottom, that the airfoil deflects the air downward over a top. It does on the bottom too, but a lot more over the top. So you're getting this downward deflection in terms of the average kind of motion of the air over the airfoil. So that downward deflection, which is essentially acting with the pressure and velocity changes to create a pressure velocity field that creates lift, or the pressure due to the imbalance in forces, is in accordance with Newton's third law, which says for every action there's an equal and opposite reaction. And when the problem is that and we'll talk about how we got here, but a lot of things you'll see that are trying to explain how Newton's third law actually works with a wing will start talking about air deflecting on the bottom and then hitting the airfoil, and the airfoil bounces up like the air is bullets, and it's not. And if you look at the streamlines, that's showing you that's not really happening. Now, I'm not saying the air is not hitting it. There's a little area called the boundary layer where that is occurring, but actually that's right at the surface, and even as you move just molecules away, it's not happening. The molecules are essentially sliding down the wing. So the gross, essentially the velocity direction, is that the airflow is moving and it's curving over the top, and it's curving down a little bit at the front and the bottom, but it's not really bouncing off the bottom and creating lift that way. The reaction that you can equate to Newton's third law is the overall downward deflection of the flow that occurs as the air flows over the airfoil, both on the top and the bottom, but mainly over the top. The problem is, and the reason we're seeing a lot of explanations that are incorrect, is we all grew up in the space age. And how do you explain rocket engines? Well, you explain rockets and how they work by Newton's third law, blowing up a balloon, letting it go. And of course the air thrusts out the bottom, or in the case of a rocket engine, the rocket engine combusts hot gas out the bottom, and in reaction to that, it pushes on the vehicle and creates a velocity or an acceleration of the vehicle going up. So these are two different examples of Newton's third law at work, but the physical mechanisms are somewhat simpler, but they also are very different. And so don't confuse the two of them. The streamlines on an airfoil show you the velocity and essentially how the air is acting. And so if you're looking for an explanation of Newton's third law and how it works with an airfoil, it's the overall downward deflection of the air that occurs as the air curves over the top, as we've already shown you. So what I'm really trying to say with this is that the physical processes, if you want to talk about the actual physics involved with the creation of lift, you can't really separate out the effects of Bernoulli and Newton's second and third law. Now, what I haven't talked about and what people miss is they treat Bernoulli as if it's something different than Newton. But as I stated early on, it's not true at all, because Bernoulli's equations are based on conservation of mass and energy, essentially Newton's second law. And the third law creeps in, though it wasn't actually involved in the Bernoulli, the generation of the equations. But there is, in the flow field, there are changes in velocity and there are changes in pressure, and there's conservation of momentum, and this is all happening in a very complex and interdependent way, because in any point in this flow field, every point actually, that pressure and velocity relationship is based on what's happening before it and a little bit on what's happening after it. In other words, the relationships within a flow field tend to be reciprocal. We always try to explain them as linear because that's trying to keep it simple, but actually it's a little too simple if you're really looking at the physics of this whole thing. And one of the ways that I try to separate this out is a lot of Bernoulli's based equations, we kind of treat the wing and the airflow as if they're separate. And that's how we get into these totally linear explanations of what goes on. And yeah, the Bernoulli's equation, or like the lift equation, is fairly simple. But the way that I think of it is, you think of a wing and an airflow as a system. In other words, if you pull the two of them apart, you don't get the same reaction at all. You put them together, and now they're like two people in a room that are interacting, or two creatures that are in the same place, if you want to think of them that way. But they become a system because each one affects the other. And while a lot of the Bernoulli's equations are correct, in the lift equation, like I'm showing you here, lift equals 1/2 times rho, which is the density, a coefficient of lift, which is a dimensionless coefficient determined in the wind tunnel for each airfoil section or shape, times the velocity squared. That's a simple equation, and it gives you the right answer, but it doesn't explain the complex physics and the fluid mechanics and the reciprocal effects and all those things that are actually happening in the flow field. And this is actually, the flow field around an airfoil is actually a very large flow field. And it goes out for some distance above and below. I tried to show that with this little graphic here that shows the minuses for the low pressure area and pluses for the high pressure area. And of course, the strongest effects or forces will be at the surface of the airfoil, and then they'll diminish as you move away from the airfoil. And one of the things we haven't talked about, of course, is, anytime you disturb any kind of an air mass, it's going to try to go back to its equilibrium state, whatever that was, and which is why, if you have an airplane that moves past you, or that it'll disturb the air and then it'll all damp out. So we've talked about an airfoil, and we've kind of talked about Bernoulli's and Newton's and how they play together to create lift, and we need to talk about one or two more things before to understand how all this works with the wing, because it becomes different, because we now move from essentially a two-dimensional picture, which is what an airfoil is, to a three-dimensional wing, which is where we live in the real world. And this extra dimension and what's going on in that flow field that the airfoil is creating introduces a change in the airflow around the wing. Now, air always flows from high pressure to low, and as I mentioned earlier, the wing is generating a high pressure area underneath itself, And so the high pressure air is trying to equalize, as I just mentioned. And so one of the ways it tries to do that is by moving around the wingtips to that low pressure area that the wing's generating on top of it. Now that creates kind of some vortices, essentially like two horizontal tornadoes spinning around the wings toward the fuselage. Now that third dimensional airflow actually affects the air going over the top of the wing and changes the flow field slightly. And what I'm trying to show you with this vector relationship is that it actually affects the angle of attack of the wing. And it causes a decrease in the angle of attack, and the angle of attack is the angle between the relative wind, which is essentially the air hitting the wing, and the angle is measured between the line called the chord line, which goes from the leading edge to the trailing edge, and that's where, and all the forces on this little drawing, you see them all come together on the wing, on that chord line. That's at the aerodynamic center I mentioned. So it reduces the angle of attack. Now, lift is essentially perpendicular to the relative wind, and essentially this airflow affects the relative wind. And what it does is it actually creates a reduction in the angle of attack, and so if that happens, two things occurs. It decreases lift and it increases drag. Now this drag is because the lift vector actually rotates back a little bit. And so now you've got part of that. If you draw the forces in that rotated lift vector creates, well, lift is straight up countering gravity in this case. We're assuming we're flying upright. And then the drag now is back toward the back end of the airplane. That's the actually lift force that's creating that drag. And lift due to drag, or I'm sorry, drag due to lift is called induced drag. So anytime we have a wing that's creating lift, it's also going to be creating some induced drag. Now, when you are flying in the air, I mean, the effect is fully developed because the wingtip vortices are fully developed. But when you get the airplane, you're starting to land, and this is especially true with a low-wing airplane that's closer to the ground when the airplane is starting to land. And you get within about a half wingspan of the ground, those vortices can't fully develop. And because they can't fully develop, the effect that rotation is creating, those vortices are creating, is reduced. And so you get an increase in lift and decrease in drag. Doesn't mean it completely goes away, because it doesn't, but they are inhibited and they can't develop like they normally could. Now, that overall effect is called ground effect, because it only happens when you're within a half wingspan of the ground. And the problem for pilots is that if you load your airplane up at or beyond the gross weight, essentially you can get an airplane and make it so that you can take off. You'll get off the ground, but you won't be able to climb out. And because as soon as you get beyond that half wingspan of the ground, now the vortices around the wingtips fully redevelop, you get a lift decrease and a drag increase. And if you're already on the margins of performance when you take off, that can be enough to essentially prevent you from climbing away. And that's why pilots spend some time learning about ground effect and how to avoid it. Now here's another piece that we want to talk about, because this is also where a lot of the explanations about Bernoulli's kind of go wrong. And this vorticity around the wing is called downwash. Now, from an engineering standpoint, when we look at airflows, we can call any downward turn of air downwash. In the pilot community, and generally, when you're talking about, even from an engineering standpoint, about aerodynamic flows around an aircraft, where when people talk about downwash, they're talking about this vorticity around the wingtips. That vorticity is a result of the wing creating lift. It is not part of the mechanisms involved in the actual creation of lift. It's a result of the wing creating lift. And the strength of that vorticity is directly proportional to the aircraft's weight. And of course, that's why when you get around these big heavy airplanes and you're flying a little airplane, you get concerned because those vortices can be really, really intense and actually cause you to lose control of your aircraft. And because the downwash that we're talking about here, this vorticity, decreases lift and increases drag, well, engineers try to minimize it. Now, if this was involved in the creation of lift, engineers would not be trying to minimize it. So that ought to tell you right there that it's not, that the downwash in the way that it's typically used is, that term is not associated with the creation of lift. It is a result of the creation of lift. And then the drawing here, we show one way that engineers try to reduce the effect of downwash, or that vorticity due to the vorticity around the wing, and by using winglets on large commercial aircraft, because if they can reduce that vorticity, can't totally eliminate it, but if they can reduce it, they'll get an increase in lift and decrease in drag, better fuel economy, and so forth and so on. So how do we get here? Well, if you go back, I think, and I think I became aware of this maybe a year or two after it started happening. In 2002, some physics teachers published an article in the Physics Teacher that said Bernoulli's was an incorrect way to teach aerodynamics, and only Newton's laws need to be used. There are some fundamental problems with that we're going to talk about in a minute. The first thing that ignores is Bernoulli's equations are derived using Newton's second law, and you can use, for simple flows, Bernoulli's all by itself to calculate lift, like we do in the lift equation. Now, once you get into an engineering / calculus-based approach, then you can use momentum exchange using Newton's laws to calculate the forces, including lift, in a wing airflow system by itself. And you don't talk directly about Bernoulli's, but the effect is still there. So when you talk about Bernoulli's, you kind of hide these momentum effects. And when you talk about the momentum exchange, you hide the Bernoulli effects. You still get the right answer in either case. Now, if you want to talk about the actual best mathematical way to calculate aerodynamics flows, and especially complex flows, you use a version of what's called the Navier-Stokes equations, which is easier to do today. When I went through engineering, this was something that really wasn't done a lot because we didn't have the computational power to do it easily. Now we have computers and stuff, and we use it a lot. And in fact, the whole field of computational fluid dynamics uses the Navier-Stokes equations to give you good answers, not totally accurate necessarily, but good answers for even very complex flows, including supersonic flows. That's way beyond where we want to go when we're trying to explain beginning students, pilots especially, this because we don't need to know that as pilots. I mean, it's nice to know all that kind of stuff. That's why I'm talking about it. But really, I'm just trying to explain this whole Newton-Bernoulli relationship and some of the problems with it. And this is where I think this all started. And unfortunately, these misperceptions about Newton's law that this whole discussion started in, and you'll see articles on the web that say, well, scientists and engineers are arguing about this. No, scientists and engineers are not arguing about this. The controversy has been in the educational end of the field, not the engineering end of the field. And that's another thing to understand about this. So when you see that kind of thing, that's incorrect. It's like we've understood all this stuff for a while. Now, I will tell you that if you there's a book, a recommendation I have about Doug McLean's book, which is a kind of really technical read. If you're an engineering student, you'll get along with it. You may not if you're not, but most people can go into Chapter 7 and essentially go look at it. Talks about the different things that are wrong with different approaches to lift, the explanation of creation of lift. Anyway, when I think probably what went wrong was that when you start talking about just using Newton's laws, the explanations that I've seen really, not totally, but almost totally, completely ignored Newton's second law. And in the layman's explanations that have tried to incorporate Newton into it, what they tend to do is they tend to grab Newton's third law, but the wrong mechanics. And that's why I talked to you earlier about public perception and why I think we're seeing these bullet explanations, like air is a bullet, which was essentially one of Newton's first assumptions, but now we know is incorrect. And I also think it's tied to the public's familiarity with the science of rocketry. And so people are trying to grab that explanation because they know that's correct, but what that misses is that the physical mechanisms between those two things, and how a wing creates lift and how a rocket engine creates lift, yeah, they're both using Newton's third law, but the physical mechanisms and how you get there are very different. And so you see, even in FAA materials, pilot education materials, they're talking about reaction air hitting on the bottom of an airfoil as part of the explanation. Wrong. Go look at the Streamlines. That'll show you that that's not true. And even if you go down to the boundary layer, and we talk about the stagnation point where the air stops, it really doesn't. But what you're really saying is that if you look at a molecular level impact at the surface, and you look at the average velocity, even though the molecules are really bouncing around, the actual average velocity is 0. So it acts like the air is coming to a stop, and it's really not. And I've also seen explanations, and there's one close to me in a museum here, where they talk about Newton's third law being a reaction to the downwash, and we're talking here about the downwash, not the downward turn of air over the top of the wing, but the downwash associated with wingtip vorticity. And as I've shown you, downwash due to wingtip vorticity reduces lift and increases drag. So don't confuse that with the airfoil's overall downturn of the air when it's creating lift. They are not the same. So just to kind of go over some of these things, these misconceptions that are out there, Bernoulli's principle, Newton's third law, they're not mutually exclusive. They're not competitive. You really, if you want to understand the physics, Bernoulli's principle talks about pressure-velocity relationships. Can't talk about lift without talking about them. Newton's third law, okay, it's involved everywhere. We've just talked about it in terms of looking for a kind of a simplified explanation. And if you look at creation of lift over an airfoil, the simplified explanation that talks about Newton's third law is the overall downturn of air that the pressure velocity field creates. And in reaction, or in reality, that downward turn of air has some accelerations and things of its own, and it feeds back into the pressure velocity field, and it is an essential part of the creation of lift. And you can't disconnect all this stuff. It's all a piece of the puzzle. Now, because we were using Bernoulli-based explanations, and people are trying to explain, well, why does the air move over the airfoil? One of the things that popped up was what's called the equal transit theory. And I know I've heard this, and I think I probably even read it as a beginning pilot many, many moons ago. Air at the top of the airfoil has to get there because it goes faster because nature abhors a vacuum. It has to get there at the same time as the air on the bottom. Well, yeah, intuitively that seems to make sense, but it's really not what's happening. And And if you'll go, there's this video link here. There's a video on YouTube you can look at, and if you essentially can show streamlines actually occurring, which can be done with oil or smoke and that kind of thing. And what you're going to see is that the air over the top of the airfoil actually gets there first. It's the pressure gradients that determine how fast the air moves. And of course, the question I'm saying here at the end of this second bullet here, talking about equal transit, is what comes first, velocity gain and pressure drop. And this is all interdependent. It's kind of like talking about the chicken and the egg, right? It's all, it kind of depends on which one you want to focus on. But all those relationships and every relationship in that pressure velocity field is really kind of circular, which sounds funky because especially, a lot of scientific discussions, you're talking about thermodynamics, it's like, well, there's no such thing as, the continuing loop that just runs itself without loss. The other big myth, Newton's third law illustration, is illustrated by wing reacting to the air bouncing off the bottom or reaction downwash. Both of those are not true. We've already discussed that. And then the other big bugaboo that's out there by one major organization is Coanda effect is involved in the creation of lift. It is not. The Coanda effect is dependent on a focused high stream jet of air close to an object. That is not the same as what's happening in a free stream airflow. And there's also a factor of air entrainment that has to occur. Now, I'm not saying the Coanda effect isn't used somewhere in aerodynamics. You can go look up a NASA paper that shows you that you can use the Coanda effect to essentially generate more lift out of like a flap system. But the way you do that is by taking bleed air from a jet engine and pumping some high-speed jets over the top, and then that does induce more extra lift, puts more energy in the airstream because you get air entrainment by the flap, created by the flap, but it's not involved in the generation of lift. And my little airplane or any other little airplane that you're probably flying has nothing to do with it. Okay. So here's a summary. I'm not going to go through it all. Essentially, the one thing I will mention is if you kind of want to understand why I generated this particular briefing, I put an introduction to aerodynamics for pilots video up on this site, and that explains where I'm coming from, and it talks about this presentation in the aerodynamics for pilots one that I did. If you don't want to take my word for it, don't. Go get a book called Understanding Aerodynamics, Arguing from the Real Physics by Doug McLean. He talks about all this stuff, and I will tell you it's a very technical read. It may lose you if you're really not into science or engineering, but most everybody can pick up chapter 7, which is talking about all this stuff about the right ways and the wrong ways to explain it and understand it, and probably get through it without all that. But I got to tell you this, he talks about in here, one of the things he says is that, when you're an engineer and you come up and you learn all this stuff, you don't really see the physics. And that's absolutely correct, because, when this started happening even as an engineer and a pilot, I had to really get into it to look at what was happening and to understand it myself. And most of my explanations were Bernoulli's based, but the ones that weren't, guess what? They were all mathematical. And so in approaching things that way, you kind of missed some of the actual physics that's going on, even though you can get out there and you can calculate all this stuff and come up with the right answer. So if it's fuzzy for engineers, sometimes don't worry if it's fuzzy for you, especially if you're not an engineer. I hope this has made a difference in your understanding. Unfortunately, where things are right now, if you're a flight instructor, you're going to have to teach students the FAA's answer to stuff until they get their pubs corrected. I don't know when that's going to be. I actually have approached them about it. I don't think I got anywhere with them. Same thing, even some of the alphabet organizations have pilot uh, educational materials that are incorrect in this sense. Go dig on to your own and go find the right answers. And I guarantee you they're out there. But I hope you'll keep in mind what I've shared with you today. And thanks for joining in.